Okay, yeah, great. So we'll we'll continue our stream for today. What is your agenda? What is your aim? Obviously, you viewers will do their productive work. You can also follow the CP theory or the book which I'm following for understanding CP for becoming better at CP. And we are at section 3.2.2 of CP3 book, which is written by Stephen and Felix. And yeah, so yeah, that will be the short introduction, and we'll continue our work. So what's the title? The title is Recursive Complete Search. Simple Backtracking UVA 7508 Queen Stress Problem. So yeah, as usual, we'll first read the question rather than just uh, downright uh, reading the theory or reading the solution. Okay, so 750. Let's read the question. Okay, 8 queens chess problem. In chess, it is possible to place 8 queens on the board so that no queen can attack can be taken by any other chess piece. No, not by any other queen. Write a program that will determine all such possible arrangements for 8 queens given the initial positions of one of the queens. Okay. Do not attempt to write a program that evaluates every possible 8 configurations of 8 queens placed on the board. This would require 8 raised to the power 8 evaluations and would bring the system to its knees. There would be a reasonable runtime constraint placed on your program. Okay, yeah. Input the first line of the input contains the number of datasets and it's followed by a blank line. Each dataset contains a pair of positive integers separated by a single space. The numbers represent a square on which one of the 8 queens must be positioned. A valid square a valid square will be represented. Uh, it will not be necessary to validate the input. Okay, that's great. Okay, to standardize our notation, assume that the upper leftmost corner of the board is position 1, comma 1. Rows run horizontally, and the top row is 1, row 1. Columns are vertical, and column 1 is the leftmost column. Any reference to a square by row then column, thus square 4, comma 6 means row 4 and column 6. Each dataset is separated by a blank line. Output. Okay. Yes, the sample input below produces four solutions. Now, the full 8-byte representation of each solution is shown. Okay. Okay, this is interesting. Submit only the one 8 digit represent. Okay, we'll read the output as well. Output for each dataset will consist of a one line per solution representation. Each solution will be sequentially numbered 1 to n. Each solution will consist of 8 numbers. Each of the 8 numbers will be the row coordinates for that solution. The column coordinate will be indicated by the order in which the 8 numbers are printed. That is, the first number represents 0, in which the position is. Uh, okay, I have got it. The first number represents the row, okay, in which the queen is positioned in column 1. The second number represents 0, in which the queen is positioned in column 2, and so on. Hmm. Okay. Actually, didn't get it. Okay, we had to print all the solutions possible. Okay, okay, I didn't know this. Okay, do not submit part of your solution. Okay, to the sample input. Okay, our queen is at this position. Okay, okay. So in column one, our queen will always in column one, our queen will always stand at row one. Okay, because this is the given input, and then and these are the variations for for column two. The queen may stand at 5, 6, 7, 7. Okay, 5, 6, and 7. Okay, is this is this is pretty interesting. Now, how do I actually approach the how do I actually approach the so this problem? One thing which we can do is you know place queen on in all of the possible cells or on all of the possible positions of the chessboard, and then we will check if if one of the queens is attacking any other queen. If yes, then um, the given chessboard is not a valid solution, and then we'll move on and we'll permit through all the positions. We'll permit through all the positions of the chessboard, but will it be feasible? I don't think so because uh, there are I guess 63 squares left. A chessboard is of dimension 8 by 8, and we have to select 7 positions out of these 63 because one of the position is already being selected or is already being given by yeah the one of the position is already been given to us by our by the input. Yeah, okay. So let us first understand when will one queen attack any other queen. As you know that a queen can move in 3 dimensions, not in 3 dimensions. The queen can move only in 2 dimensions. But what can be the directions in what can be the directions of the queen? The queen can move in the horizontal and vertical direction. The and the queen can also move diagonally. The queen can also move diagonally. Okay, so let's say there are two queens which have the same row, then they will definitely attack each other. There are two queens which will have um which will have same column, then they will definitely attack each other. So this even this condition narrows the number of permutations required. Uh, yeah, this will just reduce the number of permutations we have to look for. Okay, as of now we know that as of now we know that a queen can be a queen is already being placed at let's say row x comma y. Then what we can do is we can we can keep our queen. Mm, yeah, okay. I guess we can keep our queen at every single column. Let's say okay. Let's say the position of the queen which is given by input is row 3 and column 4. As of now, for for thinking in simple terms, we will just consider the rows. The rows should be unique. Yeah. Now let's say we are at row 1, then we can place the queen at any of the columns. So let's say we'll place it at column 1, and row 2 we can place the queen at any of the columns. So let's say we'll place it at column one again, and so on. So we have to make seven decisions. Yeah, I have to make seven decisions. Not seven, I guess eight. Okay, so let's say for constructing a board, how many decisions are needed? We have to decide seven times. Yeah, okay, this is interesting. And then at the end, after constructing the board, after keeping the queens in the given positions, we have to then we have to check the validity of the board. The validity can take, okay, for we are by following this approach, we have guaranteed that no two queens will share the same row. So we'll first of all check the columns of each and every queen. If any of two queens share the same column, then that's concerning because these two queens uh, attack each other. Draw. Let me explain what I want to say in this board. Okay, so assume yes, I need this. How do I actually add rows and columns? Shall I just import a picture? Now the only question is how do we actually recognize if now how do we actually recognize if two or more queens? Okay. I guess we can duplicate. Fantastic. You know what? Yes, I guess this is good enough to understand what we want to understand. Okay. Let me grab a pen. Yeah. What? We'll open this. We'll open this journal. Okay. Sorry, guys. The highlighter. Okay. Yeah. Yeah. I guess this is good enough. Just a second. Yeah. Yes, this is fine. So let's assume this is our chessboard. One column, two columns, three, four, five, six. Yeah. One, two, three, four, five, six. Just for simplicity, let's say that the chessboard only has 6 by 6 dimensions. One, two, 1, 2, 3, 4. 5, 6. Okay, so this is column 1, this is column 2, this is column 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So what do I actually mean by a diagonal? Let's say diagonal can be represented by, you know, um, by the difference between the two coordinates. Let's say we are subtracting uh, the row number from column number. Then let's say, okay, what will it be? Okay, 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, 3, 4, 5. What is 2 minus 1? 1 minus 2? It is minus 1, 0, 1, 2, 3, 4. This shall be minus 2, minus 1, 0, 1, 2, 3. Minus 3, minus 2, minus 1, 0, 1, 2. This shall be minus 4, minus 3, minus 2, minus 1, 0, 1. This shall be minus 5, minus 4, minus 3, minus 2, minus 1, and 0. Okay, so one thing which you can notice is that, let's say I'm talking about this diagonal. You can see that the difference between the column number and the row number is constant for a given diagonal, isn't it? So we can indeed determine. Okay, so the diagonals running from the top left corner to the bottom right corner is constant. Let's say this diagonal consists of only ones. This diagonal consists of 2, 3, 4, 5, and similarly minus 1, minus 2, minus 3, minus 4, and minus 5. Now you may ask, how will it determine, if the diagonals running from, uh, bottom right the top right to the bottom left, the diagonals, the diagonals which are of the direction, which are of the nature, in this direction, which are like, yeah, it's can be said like a line with a positive slope rather than a negative slope. So one more thing which you can observe is that the difference between these is just, the difference. Okay, let's say I have two cells uh, with the differences, with the difference between the column number and the row number being minus 2 and 0. Now the difference between these uh, between these, now the difference between uh, these two differences is 2. Then I can surely say that, the it is indeed a part of a diagonal. I can prove it to you over here. See, this is the diagonal which we are talking about. Okay, as you can see that, um, the difference. Let's call the difference. Let's say x is decreasing or increasing. Um, Depends on your perspective. Uh, and in this kind of diagonal. Okay, the x is 0 for the diagonals with a negative slope, and the x is an x is an x is 2 for this sort of diagonal. So as of now, we do know. As of now, we understand. As of now, we understand. Mm, yeah, as of now, we at least understand what's going on. I'm wondering, how can we write this in code? Okay, so what is the meaning? How much more information can we extract so that we can prove some of the more permutations? Let's take the given example. Okay. One more thing which I can think of is that a diagonal. Um, to be honest, we can also keep, okay, let me draw yet another. Okay. One, two, three, four, five, six, seven, eight. Okay. I guess I will draw now eight. One, two, three, four, five, six. Yeah, one, two, three, four, five, six, seven, eight. Okay. Okay, so what are the columns? One, two, three, four, five, six, seven, eight. One, two, three, four, five, six, seven, eight. Okay. So now we can do the opposite. We can subtract the column number from the row number. So let's say what is 1 minus 1? 0. 1 minus 2 is minus 1. 1 minus 3 is minus 2. Minus 3, minus 4, minus 5, minus 6, minus 7. 2 minus 1 is 1. 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, 5, 4, 3, 2, 1, 0, minus 1, minus 2. Okay, my bad. 6, 5, 4, 3, 2, 1, 0, minus 1. 7, 5, 4. What am I doing? 7, 6, 5, 4, 3, 2, 1, 0. Okay, so now let's talk about the diagonals which have. Okay, what am I doing? Uh, how okay, 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 it's my mistake. I thought, in this case, how I'm still wondering, how do we find out if, let's say, two given cells share a same diagonal which runs from bottom left to top right. uh, you can simply say that if the difference between them is 2 or a multiple of 2, and then I can surely say that uh, then I can surely say. Interesting. Then I guess, yeah, then I can surely say Yeah. First of all, let's think in this direction. Let's not try to, prune it more. Let's check if this will work. Okay. So, we have the idea that we don't have to worry about rows. We have to only columns. We have to only worry about the two types of diagonals. I hope you're getting me. Um, now in order to figure out if any of the two columns share a same column. Hmm. Okay, this is actually interesting. Okay, so one thing which we can do is, okay, I was just thinking about this like for a minute or two. Sorry for the delay. Um, but I guess we can use bit manipulation to figure out if, to figure out at least the column thing, you know. Okay, yeah. So let's say we will have bits. We'll use an integer. Integer will have 31 bits. We need only 8 of those bits. Okay, so we'll iterate through all the queen positions once, and then we will mark the column. We'll mark the column number. Now let's say this is bit 0, 1, 2, 3, 4, 5, 6, 7, 8. In ideal situation, uh, the columns for all of the bits should be different, isn't it? So in ideal scenario, our integer should look like this. This will take big O of 8. Yeah, this will take big O of 8, and we can simply check if if our digits, let's say not digits, if our, let's say, uh, column column state, I guess I should say, if column state is equals to 2 raised to the power 8 minus 1, then we can definitely say that um, that columns are unique and we don't have to worry about columns. Talking of the types of diagonals, yeah, the only differences which I can think of, is, yeah, the differences actually range from 7 to minus 7. Difference actually range from, okay, this is the other way around. Okay, differences actually range from minus 7 to 7. Um, yeah, so the actual differences are is 15. we can use a bit manipulation again. So for finding out the diagonals with a negative slope, we'll again use bits. Let's say 0, 1, dot 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 till 15 and 16. So, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. Yeah, yeah. No, but we have to just yeah. We will use these. Yeah, we'll use bit manipulation again. Um, for checking if a given diagonal is set or not. Let's say initially all will be unset. Yeah, all the bits will be unset if at any point during the iteration of the column, during the iteration of the, let's say, diagonal 1 type, at any point we are actually setting a set bit. It represents that there's already um, a queen which is on the particular diagonal, and yeah, I guess yes, this will do. Yeah, so we can figure out this diagonal. Okay, so this will take big of 8 again, and I actually can't figure out a way. I actually can't figure out a way to check if but not I do have a way to figure out the type to diagonal, but the thing is that it's just big of n square. Yeah, we'll iterate through each and every uh, diagonal and check if the difference between any of but the difference between any two of them is a multiple of 2. This will take like, 8 into 8. Yeah, this will need 56 iterations. And yeah, so to accommodate you know to the validity, let's say check validity, we'll have a function is valid or check validity. This function will need 56 plus 8, 56 plus 16, 72 iterations, and uh, there are 8 decisions for each row except the one. So we'll need 8 into 8 dot 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 7 times. So the actual yeah, we'll do this on new page. So as you have seen, the actual number of iterations will be 8 raised to the power 7 into 72. 72 can be written as 8 nines are 72. So 8 raised to the power 8 into 8 raised to the power 8 into 9. And I guess, yeah, this won't work. 3 are 24, 2 raised to the power 24 into 9. Yeah, I guess they have already. Yeah, this would require 8 raised to the power 8 evaluations and would bring our system to its knees. So yes, yeah, this is not it. This is not it. We are doing something wrong. Shall we just skip the columns on the air during the iteration? Why should we always complete our setup and then check for the then check for uh, then check if any of the two queens share um, a column. I guess this is I guess this is not it. This is not it. Hmm. Okay. So what is our new plan? We will we are trying we are indeed maintaining a unique row thing uh, as we are iterating through each row. Now our next target is we should maintain a unique column, on the go. Let's say if we are trying to mm, if we are trying to um if I'm trying to, let's say, put a queen on column 4, but there's another queen in column 4, but on the other but on some other row, then I can say that there's no need in even putting and calculating the other permutations. So we'll avoid same row and same column on the fly, and then at the end, mm, yeah, yeah, and then at the end we will need again 56 plus 56 plus 8, which is 64 iterations for checking the validity. Again, I guess there should be a way to do this better, but as of now, let's just think about this. Shall we just try to implement this solution and then wonder? Okay, because I don't know how many iterations are required, because we are pruning so much. We are going to prune so much permutations, because um, initially we will just put our queen, put all of our queens at, let's say, column 1, and then check the validity, and yeah, we had realized that yeah, it's of no use. um, yeah, we are avoiding this problem. I don't know what will be the actual number of positions which we are looking for. I guess yes, we will first implement the solution and check if it passes the constraints or not. Okay. So yeah, I guess we can start our implementation. Let me take a sip of water. Okay, I'm indeed live. Yeah. Let me just quickly go through. It is about 817 million possibilities now. This will TLA. Okay. Okay. So we do need a recursive solution. So the question number is UVA 750. Okay, so what are the things needed? Mm, we need a row and column of a pre-existing, yeah, queen. As of now, we'll not take an input. Let's say a row is, let's say, given. Let's say row of pre-existing queen is just 4. Yeah. Shall we call this row I and B? Row I and B is 4. Column I and B is 6. And yes, I guess, yeah. Now we have to place our queens. Hmm, interesting. Um, is there a need to? Yeah, there is a need. Yeah, vector pair int comma int. I know this solution will mostly fail, but it improves our understanding. It improves why our solution fails. Why do we need a better approach? And that is the only reason why we're trying to implement this solution. I know this problem is kind of complicated, but I guess there's no other way to understand this better than grinding to the brute force and then trying to understand how it can be made optimal, more optimal. Okay, so yeah, positions. Positions that reserve, there are only 8 queens. So yeah, positions that push back, row and p, comma column and p. Yeah, okay. And then we'll start. Okay, one more thing which is needed is int column state. This is the column state which we are talking about. Yeah, this. Yeah, I'm talking about this column state is equals to 0. Um, yep. We'll set column state is equals to column state or call input. Yeah, this is our column state. We need ind. Ind is actually a row. I will actually not select anything for the case when ind is equal to row ind. Okay, now we'll start our recursive solution. Let's just call it recursion. And yeah. Hmm. Okay, do we actually need positions? Yeah, do actually need positions. Vector int where int comma int positions. Yeah, we also need row INP. We also need column state. We also need IND, int IND. Do we need any other thing? I guess not. Even if we need it in the future, we'll just edit our file. If IND is equal to, right, shall we use one best indexing for row as well, because uh, this will just create more confusion. So we'll start IND from 1. If IND is equal to 9, then we'll print we'll print all the positions. Yeah, we'll print all the positions and then we'll simply return. Mm, yeah, I guess this is fine. Or shall we create mhm, yeah, if IND is equal to um row INP, then we'll simply um we'll simply call our next call state IND plus 1 and return. But none of these if conditions are true, then we'll start iterating for column is equals to 1 till column is smaller than equal to 8 column plus plus. But mm, if call state and if column is already set in call state, then we'll continue. But if not, then we'll set it in call state and we will call yet another recursion call state IND plus 1. Then uh, we'll unset this bit again. Yeah, is this good enough? I guess not, but let's check. And yes, okay, we will print. What can we say? Print position. This is plenty of positions, to be honest. Yeah, print position. We will have a vector of positions, and we will declare. Let's just call it queen. Let's say board and uh, hmm, and comma int. We will iterate through all the positions and then we'll set them to queen and then we'll print our board and then we'll simply return. Let's just first print not print position. We'll pass the positions. Okay, okay, a lot of positions will be printed. We'll just add a new line. Add this. Then so it will be clearer to us. Uh, and we can easily distinguish between multiple boards. I want to just check how many boards will be printed. 750. Okay, we actually didn't call the function. Position 0 IMP call state and okay, actually my bad. Yeah, this is my positions that push back. IND is 0 and yes, column. Positions dot pop back. Okay, these are indeed plenty of iterations, I guess. Shall we, shall we, print our, shall we print our output in a file? UVS 750 is an output.txt in a directory. Yes. Yeah, let's check. Okay. Mm-hmm. We are roughly at 50,000 iterations. Let me check on calculator. Yeah, 50,000 divided by 8. Oh my goodness. Um, okay, so around 6,000 iterations, and I guess we can get behind that. Not actually exactly 6,000. I guess it will be approximately 5,500 or even 5,000 iterations. Yeah, I guess we can get behind that. And for checking, we need 64 iterations. Let's say. So we need 4 lakh iterations. Yeah, 4 lakh iterations or 400,000 iterations. I guess this is fine. At the end, okay, we have to implement yet another function called check validity. Okay, so void, not void, bool, check validity. Okay, we have positions. Okay, so as decided earlier, we will have diag1 as 0 and yeah, we will have diag diagdef. Let's call them diagdef. Uh, or shall we call row called diff? Yeah. Initially, these will be only 8, and let's say the default values. Yeah, yeah. Let's say initially default value is 0. In positions, shall we 0 as well? Okay. Yes. And let's say let's call this diagdef. And what is actually diagdef? What we're just saying. Let's say column number minus row number. What is positions dot I, that second represents the yeah, this is the diagdef. Now we will try to set diagdef in diag1. What is this diag1? Represents state of diagonals with negative slope. Yeah, if at any point, if in diag1 uh, diagdef is already set, then we'll simply return false. If not, then we'll set it in diag1. My bad. Diagdef. Okay. This simple. Yeah, I guess this is fine. Okay, no. My bad. And we have to also set it in row called def. Diagdef. And this is lazy. I know this is lazy, but um, row called def dot size I plus for and j I plus row called dot say j plus f row called def absolute value of row called def dot I row called def dot j is a multiple of 2, then we return false. If nothing of these happen, then we will return true. And now we'll just add one more twist. If check validity positions, UEA75. Okay. I guess something's wrong then. Okay, I guess I made a mistake. Oh my goodness. Oh my goodness. This is actually. You know what? We'll scrape this idea just for time being. Yeah, I'll simply focus on nothing. Fantastic. Okay, so our check validity function is wrong. What is wrong with this approach? At least as of now, I can see that. Okay, I guess this is valid, isn't it? What's wrong in this? Instead of printing oh man, what is wrong with me? Yeah. One thing which we can do is bring check validity back. What am I doing? Mhm. First of all, we'll just print a row called def size. -4, -4. Am I getting confused? But the difference between any of the two. What's wrong with me? What's wrong with this? One thing which we have approximated is that only 5040 iterations are required. Iterations needed. We are making only 5040 iterations, and check whether it is again. Hmm, let's just simplicity. I know this won't make any change, but okay. So this represents all the queens are in this direction. Let's just pause this check validity function and are we right? Am I right? Yes, I am indeed right. Check validity function positions. Positions represent key positions are is there an issue when I'm trying to yeah and indeed represents a row and column represents a column. Yeah. Something's terribly wrong. Only with this. Okay, so what we are trying okay, first of all, let me just reiterate that we are trying to write a check validity um, solution. Yeah, we are trying to write a check validity function. And yeah, according to our theory, which we were discussing earlier, if the difference between any of the two, this diactive um is a multiple of 2, then I can surely say that they are, the difference between them is a multiple of 2. Okay, so let's take help of our friend ChatGPT. So I am trying to solve 8 queens problem. Here the position represents of queens on the board, one based indexing. I want to know if my check validity function itself is valid or not. One diagonal family, completely unrelated to diagonal concepts. Why? Because okay, my bad. I didn't know this. Okay, this is interesting. Let's just not accept what ChatGPT is saying. Okay, for the difference between the row column, I can definitely check. These column, these diagonals with negative slope, I can definitely check with. Yeah, but in the condition of this, let's say, okay, this is my terrible drawing. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I guess this will be fine. Let's select. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 3, 4, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, 7, 8. Okay, so let's add the row and column number. It is 2, 3, 4, 5, 6, 7, 8, 9, and duplicate one is 3, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10, 11. 5, 6, 7, 8, 9, 6, 7, 8, 9, 10, 7, 8, 9, 10, 11, 8, 9, 10, 11, 12, 9, 10, 11, 12, 13, 9, 10, 11, 12, 13, 14, 11, 12, 13, 14, 15, 12, 13, 14, 15, 16. Okay, so as you can see, these type of diagonals have constant row plus column. Okay, so yeah, I still actually don't know if Okay, so it's 0 and my goodness. Why did I make such a naive mistake? So 0 and -4 have my bad, my bad. Okay, so now I can okay, I guess you all have understood um a mistake. Okay, well again and diag 1 as 0 and diag 2 state of what can we say? Mm-hmm. Row minus column state of row plus column and yeah. Mm, shall we use an unordered map? I guess we shouldn't. I don't think. I guess we'll normalize this. Okay. So what's the what are the worst case scenarios for row minus column? What's the minimum value of row minus column? So the row should be maximum, which is 8, and column should be minimum, which is 1. So the maximum value of row minus column is 7. And what is the minimum value of row minus column? Row should be minimum, which is 1, and column should be maximum, which is 8. So minus 7. So just for the sake of simplicity, we'll normalize for diagonal. We will normalize by adding 7. As you know, there are not negative. We can't set a negative, but you know what I mean. So to be honest, we can also yeah, but this will be a full-blown dynamic programming solution, so we won't do this over here. We can, as we are maintaining a column state, we can also maintain a diag1 and diag2 state on the go. But yeah, we are currently learning about brute force solution, simple backtracking, not in complex backtracking. So we won't deep dive into that. It's not even a deep dive. We are actually implemented a dynamic programming solution. But yeah, we will we will be aligned with our syllabus. This int diag diff is positions. That's second at first. Okay. If diag1 and diag plus 7 is already set, then return false. If diag2 and diag is already set, then return false. What if they are not? Then we'll simply set them. And eventually we'll return true. Let's check whether function is indeed working. As you can see, it's not working. Okay, okay. Okay, let's just oh my goodness. Oh my goodness. What am I doing? For Diag 2 we are actually using, let's see. Okay, positions required at first. Like add tag one. Now this. Okay. I guess we are on the right track. Ma- 1, 2, 3, 4. Yeah. Yes. Thank you. I'm for some reason thinking myself. Let's see if the stream is still going on. Yes. Okay, we have been streaming for like just an hour. Okay. This question needed an hour actually. This question was it's not difficult, but once you know the actual tactic. I didn't. I have actually solved this problem, but I didn't remember this row plus column. Uh, yeah. Okay. And we have to just update this print position. I guess we'll print answer. Let's have the end comma end positions. I just actually wonder what is this? Was it mammalian? It is recommended by VHQ, so it means actually something, print answer. So what's the um you know how does our output look like? Okay, so okay, that is interesting. Okay, each solution will be sequentially numbered from 1 to n. Each solution, okay, each solution will consist of 8 numbers. Okay, each numbers will be row coordinate for that solution. Row coordinate, okay. So in column one we have this. Okay, okay, fantastic. The column coordinate will be indicated by the order in which the 8 numbers are being printed. Mhm. Okay, so we have to somehow, I guess we will use a global variable for maintaining this the number of solutions which is going on. Do we have to include as this is tab uh, int sol number, let's say, and we have to actually print. Okay, let's say if the column number is this. So what would be the what will be the okay, this is interesting. What will be the yeah, I guess a simple way to do this is I know this is kind of extra, but column, row, dect. Let's size 8 and 0 or minus. Call row dect. Positions dot I dot second is equals to positions I the first. We need, I guess, at space. Okay. Solve number. We need a tab space for int. Okay. Row dect. Yeah. I guess this is fine. And we'll print call row dect I with space and at the end and solve number plus plus. I guess we are good to go. We'll have t will input the number of test cases while t minus minus int row inp it call inp. Mm, We'll just paste this, but before we have to print this, isn't it? Um, I'm assuming these are numbers. I know I'm doing so much manual work, but I'm as of now just interested in solution. So number then again equal to 1. 1, 1, 1. Everything is 1. UES 50 will take an input. Oh, my goodness, my goodness. Why am I printing? Not print position, print answer. What? Yeah. One 7 5 8 2 4. Okay, print the solutions in lexicographical order. Oh, shall we? Shall we? Shall we maintain a vector of vector answers? Yeah. And we will, instead of printing, we'll just answers that push back call Rodic. Then we don't need any solution or anything. Okay. Okay. So what will be the rank? So what will the solution number? The solution number will actually be with this. I guess we will need j smaller than answers dot I dot size j plus plus, and eventually will answers I j. Okay, this should be done after sorting answers in. Okay, I guess we need an extra. Okay, 158637241683742517837425174 17468 1758246. I guess yes. I guess we are good to go. The only the two lines of radius is shown in the sample output and print the solutions. Do we have to actually uh each dataset is separated by a blank line. Nice. No. I'm out here. I guess we are good to go. We'll print. Let's say there are two test cases, and in one of the test case we have a queen on 4,6. Yeah. Okay. And one thing which you have to do is answers clear. Yeah. Interesting. Let's just. I'm just afraid of the error, presentation error solution. A presentation error. I guess we're good to go as of now. Please don't give a wrong answer. I'm kind of nervous. Ah, fantastic. What is going on? Let's just ask ChatGPT. Okay, first of all, we'll check our check validity function. I guess this is all right. Missing column check. Okay, so this this will be during the mm, yeah, I'm indeed checking validity too late. Yeah, I'm fine with that. Pruning partial. I don't mind that. Modify recursion so that my check validity is never needed. I know what I'm doing over here. Let's say okay. First of all, I'm kind of skeptical about the discuss 4,6, and we won't print the answer. We will print the actual. Mm, we'll print the actual position. I'm to take a look at the positions. I died a hard time. Okay, I guess, and we'll print it in output.txt. I made some mistake. I guess I'll come back in a minute. Okay, let's check first how they are printing their solution. Okay, print of okay. Okay, so they are printing this each and every time. And as usual, if k is greater than 0, okay, okay, we will not print position, we will not print our actual answer. I guess, I guess this shall be fine. Yeah, there's, uh, let's print this solution. I guess we were not printing uh, the first two columns. That may be the reason why we were getting wrong answer or WA. User solution pretty slow. Presentation error. Okay, okay. This is fine. Okay. I actually don't know how to. I'm really sorry. But I can't help. I really, really can't help. It is annoying. How many? Oh, okay, a space and then I guess. I guess yeah, a space and then a tab. I guess yeah. We will have. Um, do we have a space between? Okay, there's indeed a blank space between. Yes, yes, and then we'll have one, two, three, 6, 7, 8, and then ah, yeah, I just forgot semicolon. And do we have to actually maintain a blank space? I guess we have to. No. Let's check. Again, presentation errors. Okay, I guess we'll ask ChatGPT if our question is logically correct. If our solution is logically correct. The solution is logically correct. Okay. Important distinction, yes, it is correct, not really. Is it optimal and well designed? Yes, I understand what you're speaking, but yeah. If let's check if the actual solution in CP3 book uh mentions okay there I have printed EP. Okay, I guess our solution is good enough. I agree that there might be presentation error, but is it actually necessary in this day and age? Back in the time, presentation errors used to be a thing, but I don't. But in Code Forces and uh, but in Code Forces and other platforms, other current platforms which are being used, actually presentation errors are not a big deal. Uh, yeah, that is it. So yes, I guess we will move on. We will move on. The single most important thing was that we actually understood now what is going on, isn't it? I guess that was pretty important. Yeah. A more challenging backtracking problem, UVA 11195. Okay, let's read this question number. I guess the n queen problem is known by every person who has studied backtracking. In this problem, you should count the number of placement of n queens on an n cross n board so that no two queens attack each other to make the problem a little bit harder or easier. Uh, there are some bad squares where queens cannot be placed. Please keep in mind that bad squares cannot be used to block queens attacks. Okay. If even if two solutions become the same after rotations and reflections, they are regarded as different. So there are exactly 92 solutions to a traditional 8 queen problem. The input consists of at most 10 test cases. Oh, okay. Each case contains one integer n. Okay, 3 in the first line. The following n lines represent the board where empty squares are represented using dots and bad squares are represented using asterisks. The last case is followed by a single zero, which shouldn't be processed. Okay, let me ask you a simple question. Uh, what will be the naive way of doing this? The naive way of doing this is actually trying to, permute, even with pruning, yeah, even with enough pruning, actually trying to, find all of the possible solutions to a normal n cross n board. Okay, there are some bad squares. Okay, there are some bad squares. Okay, okay, okay. This makes okay. This is interesting. Okay, so what I was trying to think was that, let's say there is only a single bad square. There are there is there is at most one bad square. Okay, so we'll place a queen. Mhm. Okay, this is kind of difficult. Mhm. Okay, we are actually live for 2 hours now. Okay, that is good. It's actually already 1:25. Okay, I guess. Okay, we need another. Yeah. Okay, we will again get TLE for. We'll again get TLE for the solution which we're thinking of. Trying to place queens on the asterisk itself. Let's say there are two asterisks. So we'll put our queens. Yes, we'll put our queens at one of the two asterisks, then another asterisk, and yeah, somewhat in those lines, somewhat in those lines. But I guess this is a pure DP question, and as of now, we are just trying to understand about backtracking itself. We are not trying to understand DP. We are trying to understand what brute force is. Um, like what is a complete solution. So I guess we can safely skip this question as of now, and we will revisit this question when we will be in chapter 8. Yes, more challenging. Let's just highlight this question. Yeah, in blue color. Um, Okay, so we'll read remarks about complete solution programming. Okay, we'll read till this section or this point, and then we'll end our stream. Uh, I will have my lunch and then I will come back and we will continue streaming. Okay. So yes, 3.2.3 tips. The biggest gamble in writing a complete search solution is whether it will or will not be able to pass the time limit. If the time limit is 10 seconds, online judges do not use large time limits for efficient judging, and your program runs in approximately 10 seconds on several test cases, can be more than one, with the largest input sizes specified in the problem description. Yet your code is still judged to be TLE. You may want to tweak the critical code in your program instead of resolving the problem with faster algorithm, which may not be easy to redesign. Yeah, absolutely. Here are some tips you may want to consider when designing your complete search solution for a certain problem to give it a higher chance of passing the time limit. Writing a good complete search solution is an art in itself. Yeah. Okay, so what is the tip one? Step one: filtering versus generating. Programs that examine lots of, if not all, candidate solutions and choose the ones that are correct or remove the incorrect ones are called filters. The naive 8-coin solvers with 64C8 and 8 raised to the power 8 time complexity, the iterative solution for UVA 725 and 11742, etc. Usually filter programs are written iteratively. Programs that gradually build a solution and immediately prune invalid partial solutions are called generators. Example: the improved recursive 8-coin solver with its time complexity of big O of n factorial complexity plus a diagonal checks. Usually, generator problems are easier to implement when written recursively as it gives us greater flexibility for pruning the search space. Generally, filters are easier to code but run slower, given that it is usually far more difficult to prune more of the search space iteratively. Do the math complexity analysis to see if a filter is good enough or if you need to create a generator. Okay, so while talking about a complete search, okay, complete search, first of all, we have to understand that complete search is a paradigm in itself. Okay, and there are um, two types of solutions in complete search. The first one being filtering. Okay, so we'll try to generate, or if not all, at least most of the candidate solutions, and then we will filter out the unwanted ones. But these problems are usually slower, but actually they are pretty easy to implement according to this book because it is easier to write. It's a qualitative function rather than pruning while recursion or iteration itself. And the generating solutions are pretty much the opposite. We're trying to prune. Let's say we are trying to place one of the queen in a location that doesn't safe for the queen because another queen is attacking that space itself. So is it even worth your time to place that queen and generate all the possible permutations for that place itself and reject them all at the end? No, I will just prune it then and there itself. And this type of solutions are called generating solutions. Okay, I guess this is a Okay, it is said that every program spends most of its time in only about 10% of its code. Okay, the critical code. Okay, time to prune infeasible, inferior search space early while generating solutions using recursive backtracking. See the tip number one above. We may encounter a partial solution that will never lead to a full solution. We can prune the search there and explore other parts of the search space. Example, the diagonal check in the 8-queen solution above. Suppose we have placed a queen at row 0 is equals to 2. Placing the next queen at row 1 is equals to 1 or row 1 is equals to 3 will cause a diagonal conflict, and placing the next queen at row 1 is equals to 2 will cause a row conflict. Continuing from any of these feasible partial solutions will never lead to valid solutions. Yeah, definitely. Thus, we can prove these partial solutions at this juncture and concentrate only at the valid positions where row 1 can be 0, 4, 5, 6, 7. thus reducing the overall runtime. As a rule of thumb, the earlier you can prune the search space, the better. Just let that sink in. As a rule of thumb, the earlier you can prune the search space, the better it is. In other problems, we may be able to compute the potential worth of a partial and still valid solution. If the potential worth is inferior to the worth of the current best found valid solution so far, we can prune the search there. Utilize symmetries. Some problems have symmetries, and we should try to exploit symmetries to reduce execution time. In the 8 coins problem, there are 92 solutions, but there are only 12 unique or fundamental or canonical solutions, as there are rotational and line symmetries in the problem. You can utilize the fact that by only generating the 12 unique solutions, if needed, generating the whole by rotating and reflecting these 12 unique solutions. Example rows, yeah, is the horizontal reflection of the configuration of figure 3.1. Because to be honest, I don't completely understand this point. Um, yes, yeah, I kind of get it, but I don't completely get it. However, we have to remark that it is true that sometimes considering symmetries can actually complicate the code. In competitive programming, this is usually not the best way. We want shorter code to minimize bugs. If the gain obtained by dealing with symmetry is not significant in solving the problem, just ignore the step. Fantastic. Pre-computation, aka pre-calculation. Sometimes it is helpful to generate tables or data structures that accelerate the lookup of a result prior to the execution of the program itself. This is called pre-computation, in which one trades memory or space for time. However, this technique can rarely be used for recent programming contest problems. I don't know what does the author mean by recent programming contest problems, because this book is like 12 years old. For example, since we know that there are only 92 solutions in the standard 8 queens chess problem, we can create uh, a 2D in solution, okay, and then fill it with all valid permutations of the 8 queen row positions. That is, we can create a generator program which takes some time to run to fill this uh, 2D array solution. Afterwards, we can write another program to just, to simply and quickly print the correct permutations within the 92 pre-calculated configurations that satisfy the problem constraints. This I get it. I get what does the author mean, but it just feels a bit different, to actually calculate all the possible solutions and then print them as per our need. Okay, yeah, this is valid as well. We are actually kind of doing the same in this solution, or in this recursive solution, as column state is actually, it's not a data structure, but it helps us to look faster. Yeah. If I try solving the problem backwards. Some contest problems look far easier when they are solved backwards, from a less obvious angle, than when they are solved using a frontal attack from a more obvious angle. Be prepared to attempt unconventional approaches to problems. This tip is best illustrated using an example: UVA 10360 rat attack. Okay, do I have to actually solve this? Imagine the 2D array, okay? Okay. Optimizing your source code. There are many tricks that you can use to optimize your code. Understanding computer hardware and how it is organized, especially the input output, memory, and cache behavior, can help you design better code. Some examples, not exhaustive, are shown below. A biased opinion: use C++ instead of Java. An algorithm implemented using C++ usually runs faster than the one implemented in Java in many online judges, including UVA. Some programming contests give Java users extra time to account for the difference in performance. For C or C++ users, use the faster C style scanf printf rather than C in and C out. For Java users, okay, I'm not a Java user. Use the expected big of and login, but cache-friendly quick sort in C++ is still algorithms sort rather than the true and login, but non-cache friendly heap sort. Eh, Okay, this is a good tip. Access a 2D array in a row major fashion, row by row, rather than in a column major fashion. Multi-dimensional arrays are stored in a row major alternate memory. Okay, this, I didn't know about this. Although 2013 CPU can compute 100 million operations in a few seconds, 2621 million operations will still take too long in a context. Um, Okay, fantastic. Bit manipulation on the built-in integer data types up to 64-bit integer is more efficient than index manipulation in an array of booleans with bit mask. Yeah, 2.2. I solved this section, and yeah, bitmask is of great help. Instead of the arrays, bitmask seems to be more smooth, and to be honest, I feel like a bit of a pro myself if I use bitmask instead of plain arrays. If we need more than 64 bits, uses C++ as stale bitset rather than. Okay, I'll keep this in mind. Vector bool. Use lower level data structures or types of at all times if you do not need the extra functionality at the in the higher level or larger ones. For example, use an array instead of slightly larger slightly than the maximum size of the input instead of using resizable vectors. Okay. Also use 32-bit ints instead of 64-bit long longs. As the 32-bit int is faster in most 32-bit online judge systems. I don't know about this. I guess we can use long pretty often in 2026. For Java, use the first array list rather than a vector. Okay, note, and this book will stick with vectors to avoid confusion and to avoid confusing bilingual C++ and Java readers who use both C++, stale vector and Java vector. And declare most data structures, especially the bulky ones. Example, large arrays, once by placing them in the global scope. Okay, actually, I held a contrary belief to this. I guess one of the teachers in my college advised not to use global variables. I actually don't remember the reason, but I guess it was. I guess it would be because sometimes we don't reset the global variables as per our need. Like in this solution, I actually forgot to um clear all the answers. Then moving forward with the next test case. Yeah. Declare most data structures. Yeah. Okay, we have read this. When you have the option to write your code either iteratively or recursively, choose the iterative version. Example, the iterative C++ style experimentation and iterative subset generation techniques using bitmask shown in section 3.2.1 are far faster than if you write similar routines recursively, mainly due to overrides in function halls. Yeah. This the recursive functions take up a lot of stack space, and that is usually not good. Array access array access in nested loops can be slow. Okay, if you have an array A and you frequently access the value AI without changing it in nested loops, it may be beneficial to use local variable temp AI and work with temp instead. In C or C++, appropriate usage of macros or inline functions can reduce runtime. Appropriate is keyword over here. Yeah. For C++ users, using C-styled arrays will yield faster execution than using C++ as field string. For Java users, okay, browse the internet or relevant books to find much more information on how to speed up your code. Practice this code hacking skill. by choosing a harder problem in UVA online judge where the runtime of the best solution is not 0 seconds. Submit several variants of your accepted solutions and check the runtime differences. Adopt hacking modification that consistently gives you faster runtime. Use better data structures and algorithms. No kidding. Using better data structures and algorithms will always outperform any optimizations mentioned in tips 1 to 6 above. If you're sure that you have written your fastest complete search code, but it is still judged as TLA, abandon the complete search approach. Yeah. Remarks about complete search and programming contests. The main source of complete search material in this chapter is the USA CO training gateway. We have adopted the name complete search rather than the brute force with its negative connotations, as we believe that some complete search solutions can be clever and fast. We feel the term clever brute force is also a little self-contradictory. If a problem is solvable by complete search, it will also be clear when to use the iterative or recursive backtracking approaches. Iterative approaches are used when one can derive the different states easily with some formula relative to a certain counter, and almost all states have to be checked. Example: scanning all the indices of an array, enumerating almost all possible subsets of a small set, generating all permutations. Recursive backtracking is used when it is hard to derive the different states with a simple index, and or one also wants to heavily prune the search space. Example: the 8 queens chess problem. If the search space of a problem that is solvable with complete search is large, then the recursive backtracking approaches which allow early pruning of infeasible sections of this search space are usually used. Pruning in iterative complete searches is not impossible, but is usually difficult. The best way to improve your complete search skills is to solve more complete search problems. We have provided a list of such problems separated into several categories below. Please attempt as many as possible, especially those which are highlighted with the must try asterisk indicator. Later in section 3.5, readers will encounter further examples of recursive backtracking, but with the addition of memoization technique. Note that we will discuss some more advanced search techniques later in section 8.2 using bit manipulation, recursive backtracking, harder state space search, meet in the middle, A star search. I didn't know. I don't know. A star. Depth limited searches, iterative deepening search ideas, and iterative deepening IDA. Okay, so here are some questions. Okay, we'll start with the next paradigm after this problem set. Okay, I guess we should stop first now. I will have my lunch and I will come back after having my lunch and after taking some rest, and we will have another stream which will last from afternoon till the evening. Yeah. Okay, so we'll not solve I guess each and every question because it will take a lot of time. 7 plus 7 plus 12, 19 plus 14, 33. 33 plus 17, 50, 50, 65, 78, 96, 96, 110. These are 110 problems. I guess we don't have to solve each and every problem. Uh, I will ask ChatGPT to solve only the relative problems, only the relatively important problems. And yes, I guess that was the stream today. We were just talking about backtracking and everything. We actually solved only a single question, but we did explore many concepts. We did explore many of the tips, and it was actually a very productive stream. I hope you guys learned um, uh, something important from a stream today. And yes, I guess yeah, it was a great stream. I'll come back again, and yeah, thank you.